Hello, my name is Antonio Jaime Azuara, and in this presentation I'm going to show the work I have done on monomer recovery from hydrothermal processing of condensation polymers at subcritical and supercritical conditions. First of all, I am going to give you an overview of chemical recycling, what it is, and what is its role in the plastic waste context. Afterwards, I will present the prospects of this technology. And finally, I'm gonna also show you which are the future activities that we are gonna conduct in our research group. Plastic waste is known to be a problem, and for the last years we've been seeing in the news almost every day information about the effect of plastic waste in the environment. And since China banned the importation of plastic waste from foreign countries like the European countries or the US, these countries actually they have had to look for alternative countries to send their waste. One of these countries was Malaysia, but nowadays Malaysia is also reluctant to receive plastic waste. And we have to accept that sending our waste to other countries so they handle with it is not the solution to the plastic waste problem. And also, we have to consider that when we send waste to some countries, the waste management systems can not be good enough, and our waste or the plastic waste could end up in illegal or uncontrolled landfills, and also even leak in the natural ecosystems. Of course, plastic waste is a problem, but it's also giving us the opportunity to transition from a linear economy based on take, make, and dispose to a new circular economy where recycling becomes paramount. Until now, we've been recycling plastic in a way that after each cycle of recycling, the plastic would be used in a lower value application. So after a few cycles, it wouldn't be possible to recycle the plastic anymore. So it would end up in landfills or incinerated. So that's why in some cases, people talk about downcycling rather than recycling. The circular economy presents a new paradigm in which plastic becomes waste, but it can be recycled in a way that it is used in the same kind of application without losing any kind of value, and this way we can close the recycling loop. But now the question is which are the recycling technologies that allow us to close the recycling loop? The alternative is chemical recycling of plastic waste, and this technology allows us to overcome the limitation of mechanical recycling. So, what is actually chemical recycling and where it is found within the waste management system? Okay, chemical recycling is classified as a recycling waste treatment technology, and within chemical recycling, we can find different technologies. We have one technology that is dissolution, that even though in this graph is classified as a different level of recycling, it belongs to the chemical recycling technologies. This technology chooses a selective solvent that dissolves in a specific polymer, and this way, when the polymer is dissolved, all contaminants and or other polymers can be removed. And once this is done, the polymer is precipitated again and can be melted and turned into new plastic products. Then we have another group of chemical recycling technologies that use thermochemical processes to transform the polymer into monomers or other base chemicals. Some of the challenges of these technologies are mostly the selectivity of the polymerization. Means that in a lot of cases, instead of getting a few products, the products is the composition of the product is just a pool of a lot of different chemicals. So no chemical can be directly reclaimed, and it has to be further processed. And in a lot of cases, it's turned into fuels. And we could say that this is the least preferable solution because once the plastic is turned into fuel, this is burned, and all the value of the plastic is lost. Instead, we will always want to be on the higher part of the of this graph, since we have the most preferred technology that is keeping the value of the polymer as a polymer, and then we go down to polymer to monomers, then polymer to chemicals, and then polymer to energy. And it's important to say that not all chemical recycling technologies are suitable for all kinds of polymers. And that's why it's important to divide polymers in different groups. And we've decided to divide polymers in two big groups: polyolefins, which are polymers made of carbon and hydrogen atoms, like polyethylene and polypropylene. And then we have polycondensation polymers that are polymers that in their production, molecule was released. So that's why it's condensation, polycondensation. And these polymers contain more atoms than just carbon and hydrogen. Polymerization of polyolefins stands out for having a high exergonicity. This means that a lot of energy is released during the polymerization, and this is really relevant because if we want to shift the equilibrium from the polymer side to the monomer side, we have to significantly increase the temperature. And under these conditions, the polymerization is driven by free radical random chain excitation, which means that we are not gonna be to selectively depolymerize the polyolefin into the monomer, but we will get a wide pool of chemicals that will also interact with each other and repolymerize. So we cannot. It's really difficult to control the composition of the product, and that's why polyolefins are not suitable for direct chemical recycling to monomers. So instead, the polyolefins are usually turned into a feedstock that is similar to the petrochemical, to a certain petrochemical fraction, like naphtha. Then this fraction is cracked, and then this is turned into monomers or other chemicals. On the other hand, we have polycondensates, and some examples of these kind of polymers are polyesters, polyamides, and polycarbonates. And these polymers are characterized by having polymer backbone functionalities, and these functional groups play a really important role during the depolymerization because there will be a certain polarity within the polymer molecule, and then ionic polymerization can be triggered under mild solvolytic conditions. If we find the right solvent, which will produce a nucleophile and an electrophile that triggers the cleavage of the polymer molecule, then we will selectively depolymerize the molecule. Because if we look, for example, at the bond energy of polycarbonate, we can see that there are some bonds that are more prone to be broken under thermal conditions. But by using the mild solvolytic conditions, we can avoid breaking the molecule randomly and instead breaking the molecule where we want. In this context, hydrothermal processing of plastic waste becomes an outstanding medium for selective monomer recovery. This technology uses the special properties of water at high pressure and high temperature. One of these properties is the ionic dissociation constant, that it will increase as the temperature of water is increased, and which means that more water molecules will dissociate in the proton and hydroxyl group, and these ions will attack the functional groups of the polymer, triggering a selective depolymerization. All this process is done below the supercritical point and allow us to do a selective polymerization, obtain high monomer recovery rates, and do all this with a green solvent like water. This technology is suitable for a wide range of polymers. For example, polycarbonate, one of the polycondensates that were mentioned before was subjected to 400 degrees C, 250 bar for 15 minutes, and oil yields up to 99.8% were obtained. In the chemical composition of this oil, four main chemical compounds were found, meaning that the polymerization was done in a really selective way. However, we have other polymers like styrene butadiene that is made up of carbon hydrogen atoms, and these kind of polymers don't behave as selectively as polycarbonate. As you can see in the GCMS, a wide range of aromatics was obtained with an oil yield up to 80.8%. And now I'm going to present you a specific case study that is the monomer recovery from PET by hydrothermal processing. And PET was chosen because it's one of the main polymers that is being used by European plastic converters, and it represents up to 7.4% of all the demand. This percentage is translated into 4.5 million tons of plastic every year. And it's really important to look at the application of PET as a polymer because it is mainly used for packaging. Packaging stands out from all the other applications because of its high rates of circularity, which means that it becomes waste in a really short period of time. Hydrothermal processing of PET shows really fast kinetics with high yields and monomer purities. And what we have done in our lab is to subject PET waste to hydrothermal processing subcritical conditions during 10 to 15 minutes, yielding two main product phases: a solid phase made up of TPA monomer and other intermediates, and another phase that is an aqueous phase made of water and ethylene glycol, which is the other monomer that is used in the production of PET. Finally, we found out that the optimum was to use 350 degrees C at 170 bar during 10 minutes, and these conditions yield a monomer recovery of 93%, and TPA showed a purity of 99% that was confirmed by doing HPLC analysis. Real PET waste is made of PET polymer, but also a lot of other contaminants, colorants, and additives that have to be removed from your TPA product. In our group, we are working on harnessing the tunability of subcritical water solubility to remove all these contaminants. As you can see in the graph, TPA solubility increases with temperature, and between 0 and 150, the TPA solubility in water is almost negligible. But between 150 and 250, it becomes significant, and actually at 250, all the TPA in our system will be dissolved in the water, which is really advantageous because we can then remove all the insoluble contaminants. So our approach is the following. We have a process in which we are producing a mixture of insoluble contaminants, TPA, soluble contaminants, and water and ethylene glycol. And first of all, we do hot separation to remove all insoluble contaminants. After that, we will have only TPA, soluble contaminants, and water and ethylene glycol. By decreasing the temperature, we will trigger TPA crystallization, and we will separate it from the mixture. After that, we will further cool the mixture to room temperature, and all the other insoluble soluble contaminants will finally crystallize, and they will be removed from the water and the ethylene glycol. And now it's time to jump from batch experiments to a continuous process. We are currently working on designing and building a new continuous process that will be commissioned in spring 2021. And this process will be able to recycle up to 15 kilograms of plastic waste every day. Using this process, we're gonna focus on developing new product separation and purification technologies, and this way we will reach our KPIs related to monomer recovery and monomer purity. And on the other hand, we are also gonna study and optimize the energy integration of the system, because this will allow us to get an idea of the economic and the environmental impact of the process, which will be studied by using the tools of techno-economic analysis and life cycle assessment. And this is all. Thank you so much for attending and listening to my presentation. And now I will be available for any question that comes to your mind.